Hello, we're starting section 4-6. We're going to take another look at limits. This time there are limits at infinity. So before we get started, I want to go back to our basic limits and make sure everybody remembers that when I say the limit as x goes to 3 of this function is 9, that this value right here is an x value. So if I was to graph this, I would be looking on the x-axis for that number. And then this number right here is a y value. So if I graphed it, I would be looking on the y-axis for that number. That's really important as we go forward, because what we're going to do in section 4-6 is we're going to take a look at what if this value or this value are infinity. Okay, and so you need to be thinking on the graph in the correct direction. So for example, if I say the limit as x goes to infinity of a function is something, let's say 3. Okay, what that means is as I go towards x equals infinity, so I look on the x-axis and I'm looking way out here, okay, to my big numbers. That means that the graph is going to get really close to this y value of 3. So it's coming in like this and kind of scooting along here. So as x gets big, the function settles down to this y value. Okay, now contrast that. Let me flip this phrase and say the limit as x goes to 3 of the function is infinity. So that actually means something very different. Now I'm going to the x-axis to find 3 here, and as my function grows close to this number, it goes up to a y value of infinity, so it's going up like this. Okay, that's what my function's doing. All right, so that's really important to keep clear in your brain. So let's do a couple examples. These are going to be in categories. So the first category we're going to look at is just basic power functions. And these are pretty straightforward. If you have a function like negative 4x cubed, just anything to a power, and I want to know what's the limit as x goes to infinity of this function, well, basically, you can just imagine plugging in a really big number for x. Well, what happens? As if I plug in 1,000,000 for x and I cube it, it gets even bigger. Okay, so this is getting really big. Okay, but then I'm going to multiply it by a negative 4, and that's going to turn it negative, because a positive times a negative is a negative. So this guy is going to negative infinity. That's how we write that. Conversely, if I take the limit as x goes to negative infinity, well, so this was a big positive number that we were plugging in. Now we're going to plug in a big negative number. What happens? Negative 1,000,000. Okay, well, negative 1,000,000 cubed is a negative big number, right? And that's being multiplied by a negative 4. So this actually is going to turn into a very big positive number. Okay, so the bottom line is the power just makes it bigger, so it's going to go big to infinity. But then you look at the number in front to figure out, is that going to be a negative or a positive? That's going to affect the answer. All right, so that's how you do power functions. Rational functions are a little bit more tricky, because with rational functions you have a fraction, and division makes things smaller when you divide things out. So yes, I'm getting big numbers on the top, but I'm also getting big numbers on the bottom when I plug in. And how much bigger is the top than the bottom? I mean, that's a question that we don't know necessarily. Do the 3 and the 5 impact this, and how much? And so the fractions create a situation where anytime you're going to subtract something off or divide something out, the question is, yeah, that's going to make it smaller, but how much smaller, and how fast is it going to get smaller? Is it still going to get infinitely large, or is it going to settle down into a number? So what we want to do, instead of creating big numbers on top of big numbers, what we want to do is create small numbers on top of big numbers. Because let's look, if I have a small number, so this is hard, okay? We don't know how to deal with big numbers over big numbers, but this is easy. Watch. If I have 3 over 1 million, what is that? Divide it out on your calculator. You probably go into scientific notation. This is really small. And the bigger this number gets, the smaller the quotient gets every time. There's no question about it, okay? Because you don't have anything really, this is a consistent spot, is 3, and it's not growing with the 1 million. So if we could create a number over an x, and x gets really big, then this goes to 0, okay? That's the idea. So with rational functions, your plan, you are going to divide the top and the bottom by the biggest power in the denominator. Now, if you had me for pre-calc before last semester, we did this, okay? You've seen this with rational functions. Actually, I may have done it last semester too, but we did this when we were graphing rational functions. This is how we found our horizontal asymptotes. So hopefully this looks a little bit familiar if you've had me before. If you haven't and this is new, that's okay. Just jump on board. So here's what this looks like. I'm going to take this function, 1 over 5x squared, and the biggest power in the denominator is an x squared. Okay? So I'm going to divide every term by an x squared on the top and the bottom. That's legal because I'm dividing every term. It's all even. You're not changing the value at all. So here's what happens. Look at it. Well, I'll write one more step so you can see it clearly. You don't have to write this extra step for me, but just the first time around I'll show you. You're creating all these little fractions, and the idea is because we divided by the biggest power, everything on the top is going to cancel. So look, x squared, x with one of these x's, nothing cancels in this last one. X squared, x and 1, and nothing cancels there. So what this reduces to is 3 plus 2 over x minus 1 over x squared all over 5 minus 4 over x plus 7 over x squared. Now plug in a big number for x, okay? Plug in 1 million. What happens here? 2 over a million, that's essentially 0. Okay, because the 2 is static and the x is getting huger and huger. This is getting closer and closer to 0. Here, even more so. You're going to go 1, that stays 1, but it's over a million squared, which is even bigger. This is going to 0. Okay, long story short, everything that's over x is going to 0. And these guys don't depend on x, so they stay. And your answer here is 3/5. And it turns out, if you remember from pre-calc graphing rational functions, this is where we get our horizontal asymptotes. Okay, the powers, maybe your instructor showed you the tricks. If the powers on the top and the bottom match, then it's the ratio of the leading coefficients. That's where that's coming from. But we're walking through the formal way to calculate this with algebra and why that is, instead of just memorizing the rule. Okay, let's look at another example of these. I'm gonna do 3 examples of these rational functions. So what if we have this equation. I'm going to, again, do the same trick. I'm going to divide everything by the largest power in the denominator, which is x squared. So I'm going to get 3x over x squared, 1 over x squared over x squared, and 3 over x squared. So reducing that, I get 3 over x plus 1 over x squared over 1 minus 3 over x squared. Okay, plug in a big number for x. This goes to 0, this goes to 0, and this goes to 0. And I'm left with 0 over 1, which is 0. That's your limit. Okay, one more example. All right, biggest power in the denominator is x. So I'm dividing everything by x. All right, reducing. This is going to be 3x plus 4 over 1 plus 2 over x. Now plug in, this is a little bit different than the others. Plug in a big number for x. This goes to 0. So what I've got on my denominator is 1, right, which is a static number. Now this gets really big, okay, and a big number plus 4 is still big. But what I've done is, because I divided by the highest power in the denominator, I eliminated my x terms from the denominator, essentially, because this guy goes to 0. And so now I have a big number over 1, and this is standing still, so I'm not really dividing out powers of x's. And so a big number over 1 is just a big number. So my answer is infinity on this guy. Okay, so when the higher powers are in the top, it's a little bit different. And again, watch out for your signs. It's possible that it's a negative infinity if that 3 was negative. All right, now similar trick, different group of limit functions. These are going to be radicals. The principles are the same, okay? You're still going to divide by the highest power in the denominator, but the way radicals work, let's just review something. This is sometimes a little bit weird for people, but if I take an x, let's start with numbers. So let's say I have a 3, and say it's a 3 root 2. And I want to take this 3 and I want to push it in under the root. Now, up until now, I mean, usually we talk about that's black magic. You can't push a number under a root. It's actually not black magic if you do it correctly. If you can push it under a root if you adjust the value correctly. So the way I do that is I say, well, if that 3 is going to come in here under the root and with a 2, then what number do I take the root of to get 3? So I'm kind of thinking backwards, like what makes this equivalent? And the answer is if I put a 9 under here, because the square root of 9 is 3. So this would be equivalent. It's like reducing fractions in reverse. Okay, so if I think front direction, square root of 18, what is that? Oh, that's square root of 9 times 2, and then the 9 I can root the 9 and make 3 root 2. It's that process in reverse. So I want to put this back in. I've got to square it to get it inside. Okay, and the same is true with x's. So if I want to, if I have an x here, and I want to put it in the root, I can do that as long as I square it when I put it in. Okay? All right, so, excuse me. Let's do, the other thing that we have to acknowledge also is that the square root of x squared is not just x, it's the absolute value of x. And the reason is because we got to make sure that as we're pushing these guys in and out that they are positive, because you can't root a negative. So we're going to use this principle in a minute, and let's look at a problem. All right, so my highest power in the bottom is an x. So in this case, we're going to divide the top and bottom by the absolute value of x. The reason, again, is because I want to shove it, ultimately I want to shove it under the root upstairs, and it needs to be an absolute value because it needs to be positive. Okay, so here's what that looks like. I'll do a couple of steps. I do 1 over absolute value of x on this root. And then I'm doing 1 over absolute value of x on the bottom here as well. All right, now I'm going to kind of distribute that in. So same principle that we just talked about. This x right here is going to distribute into this root, but when I distribute it in, it's going to turn into a squared because I'm pushing it under a root. So the top becomes the square root of 3x squared over x squared. Now I can drop the absolute values because now it's squared, so it is positive, okay, when you push it inside. And that's how we're getting those fractions dealt with. Now what happens downstairs? This distributes in, but the absolute value doesn't drop off because it's not squared. So I've got to keep it on there. So this becomes x over the absolute value of x, 6 over the absolute value of x. All right? And now we reduce. So this becomes 3 plus 4 over x squared. And downstairs, I'm putting in a positive big number. So that means that this, I have to look at the sign here. So this is going to be positive, and this is going to be positive because it's an absolute value. So then these guys cancel and give me a positive 1. And similarly here, I can drop the absolute values because this is positive because I'm plugging in, again, a positive big number. So this is just going to be 6 over x. But I have to kind of think through that sign thing. Okay, so again, this is because x is bigger than 0 that I can drop this absolute value. And then now I'm going to plug in a really big number. That's going to go to 0, and this is going to go to 0, and I'm left with the square root of 3 over 1, which is the square root of 3. So that's your limit there. Okay. Let's try another one. Let's try the same one, but I want to change it to negative infinity and show you how that absolute value flushes out. So hold on here. Sorry, I ran out of room. I thought I had enough pages clear. Okay, let's do limit as x goes to negative infinity of 1 over absolute value of x, 3x squared plus 4. Oh, sorry. Let me write down the problem before I distribute in. I skipped some steps in my notes, sorry. X plus c. So same function, okay? Same trick. I'm going to divide by the absolute value of x. So 8. Sorry, a little struggle here. Negative infinity. Okay, 1 over absolute value of x, 3x squared plus 4, 1 over absolute value of x, x plus 6. All right, now the deal is I'm pushing this guy in, and I'm squaring it when I push it in. So it doesn't really matter what the sign is. because I'm squaring it, it'll be a positive value. So I can pull off the absolute value, and I get the same thing as I did before on the top. The bottom's where it matters, okay? Now I'm pushing in this, well, let me do it one step at a time. This is going to be x over absolute value of x plus 6 over absolute value of x. But what I'm doing is I'm going to now plug in a negative infinity. So this is going to be a really big negative number. Okay, let's see how that affects the limit. This reduces to 3 plus 4 over x squared. And now downstairs, if this is a really big negative number, this will be negative. But this, because it's an absolute value, will be positive. So a negative value divided by the same positive value equals a -1. So that's where the negative infinity is going to change things. Okay. Similarly, here you've got a 6. That's a positive value, and a absolute value of a really big negative number is still a positive value. So this is going to reduce to 6 over x. You can drop the absolute values, you know it's going to be positive. Okay. Sorry, not x, negative x. Okay, you need this to be positive. So this goes back to the definition of the absolute value. The absolute value is you just leave it the same if x is positive, and you put a negative sign in front of it, or you change the sign if x is less than 0. So since x is less than 0, because we're going to negative infinity, you're going to replace the absolute value with a negative x, and that's going to make that term positive. All right. So what does that mean limit-wise? This is still going to 0. This is still going to 0, right? And so all I've got now is root 3 over -1, which is negative root 3. Okay. All right, here's an example to try. These root ones can be a little tricky, so try example 4.26. It's another root one, and you can see how you do with those. All right. Next classification is when we've got e to the x. We've got exponentials. Okay, and the trick here is going to be to divide each term by e to the x. So here's an example. All right, so they kind of act the same way. We have the same problem. These guys get really big. As x goes to infinity, e to the x gets really big. Remember from pre-calc what this graph looks like. Knowing the shape of the graph is going to help immensely. So what happens as x gets really big? Y gets really big. So the limit as x goes to infinity of e to the x is infinity. So the problem is I've got a big number on top and I'm dividing out by another big number. So the question is, which one grows faster? And I'm not sure, and how much faster. So again, you want to create a fraction. So that's why we're going to divide by e to the x. So 3e to the x over e to the x, same kind of trick, same reasoning. Cancel things off if you can. So this is going to be 3 minus 4 over e to the x, 5 plus 2 over e to the x, and now plug in a really big number. So when I plug in a big number, this gets really, really big, and this gets really, really big. 4 over a big number goes to 0, and 2 over a big number goes to 0. So this limit is going to be 3/5. Okay. Now be careful, because if you are going to negative infinity, this is different. look at the graph again. Here's e to the x, right? As x goes to negative infinity, where does y go? If you remember from pre-calc, there's actually an asymptote here on the exponential functions. And so the y value is actually going to 0. So these are different. When I say x goes to negative infinity of e to the x, the answer is 0. And 0 is cool. We're fine with zeros on fractions. They often work well, and we don't have to divide in this case often. Okay, so let's take a look at the same function, but with x going to negative infinity. So if I do a direct plug-in, I'm looking at this. If I plug in a really big negative number, this goes to 0 right away. It's not blowing up. And this also goes to 0. Well, the 4 and the 2 don't depend on x, so this actually is just negative 4 over 2, which equals negative 2. And that's your answer. All right, that's it. Those are all the classifications. If you want to try an example of these exponentials, 4.227 will be your guide. Try that and then jump into the homework. See you next time.